Hey, and welcome to a video on defining the derivative, or really just looking at the difference quotient and how to find that for any given function here. So a couple quick things that we need to review is maybe Pascal's triangle. So you may or may not be familiar with it from your previous courses, but let's go ahead and review it now. So Pascal's triangle was a way to expand binomials that are of the form the quantity a plus b to the nth power. And so, for example, if we raise a plus b to the 0, we end up with a 1. And if we look at the coefficients as we raise, for example, a plus b to the first, we have 1a plus 1b. And then if we look at, for example, a plus b quantity squared, just looking at those coefficients, we get a 1a squared. Then we would have a 2ab plus that 1b squared. I can also expand out the quantity a plus b cubed, but what Pascal determined, and you can do this using combinatorics as well in a probability. So if you saw it as, for example, 2 choose 1, 2 choose 2, etc., that might be familiar to you. That's the binomial theorem. So Pascal discovered this little trend here, that 1 plus 2 is 3. That'll get us our next coefficient. 2 plus 1 is 3, so it's the sum of the two that are diagonally above it. And then 1's on the end. So the next row of Pascal's triangle is going to get us these coefficients of this expanded binomial. 1 is on the end, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and a 1 on the end. And then if I wanted to see the next row, I could. I have a 1 on the end. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5, and a 1 on the diagonal. And again, this would be the expanded form of something like the binomial a plus b to the fifth. And these are just the coefficients. So what happens to our variables is, for example, if I'm looking at that a plus b to the fifth, it'd be 1a to the fifth, then a would be descending, a to the fourth, the next term would be a cubed, then a squared, then a, and then no a, and then our b's, so to speak, or our second term in that binomial would count up or be ascending. So I have no b's, b to the first, then a b squared, then a b cubed, then a b to the fourth, and then a b to the fifth. And because I was a plus b, all of these terms are going to be positive. There's no need for them to be negative. And so I've expanded this polynomial without actually even multiplying it by itself 5 times. Certainly you could do that. A plus b times a quantity, a plus b times a plus b, etc. 5 times. One last thing to just check to make sure that you have a possibility of doing this right is that the degree of each term should be 5. So I see here is a to the fifth. Then in my second term is a to the fourth and b to the first. That has a degree of 5. A cubed b squared, that adds up to 5 in terms of degree. A squared b cubed is 5 because it's 2 plus 3. Then a to the first, b to the fourth is 5, and then my b to the fifth. So that's just Pascal's triangle. That might be helpful as you're doing difference quotient type problems. Now let's look at one more thing before we remind ourselves of what the difference quotient is algebraically. Let's take a look at the slope between two given points. Okay, so let's say that I have this given function here as graphed on a Cartesian xy plane. And let's just say I wanted to find the slope between any two random points. So let's say I purposely pick out this point right here that I'm going to say is some x value, and then because I've defined my function to be f of x, I know its output or y value would be f of x. And then I'm going to horizontally shift over h units to the right. So this new value right here is now x plus h, because I've shifted my original point over h units to the right. So now my new x value is x plus h, and so my new y value would be f of x plus h. And I could write these out as points on the actual curve right here. This one was x plus h, comma, f of x plus h, and the first one was x, comma, f of x. Okay, so using just these 2 points, let's find the slope between these two. So we should remember that slope was rise over run, or change in y over change in x, which sometimes is written like so. So y sub 2 would be my f of x plus h minus my y sub 1, which is f of x, all over x sub 2, which is that x plus h, minus x sub 1, which I called x. Now, the only really thing that you should be seeing here is perhaps that this x in the denominator and this negative x add to 0. So I'll go ahead and just take that out. My numerator is going to stay the same, but my denominator will just become h. Now, we have defined this quantity right here that I will just highlight here in blue to be the difference quotient. So you may have studied this in a pre-calc course and not necessarily known why, and you're going to take a look at why in your calculus course and what it actually means. But let's just review how you find that difference quotient algebraically. So that's the first thing that I'm going to do when I go over here is I'm going to write down that difference quotient. So I'm actually looking for basically the idea of slope here. And instead of f, I named this function g. So that's perfectly fine. Instead of f, I can call this function g, and it operates the same way. So we do need to find g of x plus h. So let's look at that first. So g of x plus h means that you're going to substitute x plus h into every x that you see. And let's go ahead and expand this out. And this is the part where Pascal's triangle might be helpful to us because you see we do have to cube this binomial here. So it looks an awful lot like that quantity a plus b cubed that we looked at, or the third row of that Pascal's triangle. So if you wanted to look back and reference, here it is right here. It's the 1, 3, 3, 1. So let me show you how that works. So I've got g of x plus h. I still have this 3, which I'll distribute when I'm done. And it's 1, 3, 3, 1. And then again, your first term is going to be the descending power. So this will be x cubed, x squared, x, and then no x. And then my second term in that binomial will be ascending, so no h's, h to the first, h squared, and then h cubed. And because it was a plus in between, right, then all my signs are still positive. I can distribute the 3 in a minute here. I'll distribute that -5. And now I will go ahead and distribute that 3 just so I can remove all parentheses and get a simplified g of x plus h. Okay, and you may be wondering why you need to multiply that all out or expand it, but hopefully you'll see it here in just 1 second. So my difference quotient, again, is this g of x plus h minus the original function. So I have my g of x plus h. So my difference quotient is going to be here, this g of x plus h. So I'm going to copy down that whole gray line. So that's my g of x plus h minus my g of x. If you remember, or if you can still see it on your screen, our g of x was originally 3x cubed minus 5x plus 4. And all of that is going to be divided by h. So let's keep going here. So if I distribute this negative, maybe you don't need to rewrite everything to see it, and maybe you do. I'll rewrite it here in a second. But maybe you can see that this 3x cubed, when it's negative, is going to add really nicely to that and add to 0. But let me go ahead and rewrite it for you after I distribute so you can see it all the way through. All right, so I rewrote it all after I distributed that negative, and here we can see that the 3x cubes add to 0. I can also see that this -4 and +4 add to 0. I can also see that that plus 5x and -5x add to 0. I don't want to lose this -5h though, so I kind of circle it because everything, after this -5x got added to 0, but I don't want to lose that -5h. So I'll write down what I have left here. I have this 9x squared h plus 9xh squared and a 3h cubed and the -5h. Don't forget about that. And it's all over h. So what you should see now is that everything is divisible by h. In other words, you can factor an h out of the numerator of every term, and then h divided by h is 1. So this difference quotient turns out to be 9x squared plus 9xh plus 3h squared minus 5. That is the value of the difference quotient, which again, when you're in college algebra, you might not see a purpose for a difference quotient, but this is based off of the difference quotient is used in every single thing that we do in Calc 1. This is going to become your definition of your derivative. We're going to look at when the distance between the 2 points, when that distance becomes close to 0, you're going to see that these 2 points are going to become close to 1 point, and so you'll be able to estimate or find an instantaneous rate of change instead of only talking about an average rate of change. So this difference quotient becomes a necessary piece when we are evaluating a limit. So I hope this algebraically reminds you of Pascal's triangle and maybe a difference quotient, which might help you as you study these through your Calc 1 course. Thanks for watching.